You probably remember the periodic table from school, right? Just a big, kind of boring chart of elements. But what if I told you it's not really a chart at all, but more of a treasure map? A map that's packed with secret codes that can, believe it or not, predict the future.
No, seriously, just think about that for a second. Imagine having a map that doesn't just show you where things are, but tells you what they're going to do, how they're going to behave, even before you've ever seen them. It sounds like something straight out of science fiction, doesn't it?
Well, for chemists and scientists, that map is very, very real. It's this grid of boxes, yeah? But it organizes all the known building blocks of our entire universe. And because of how it's organized, we can spot these amazing patterns and make some truly incredible predictions. So today, we're going to decode one of its most dramatic secrets.
To do that, we're going to zoom way in on just one column of the table. We're going to look at a family of elements that has a, well, let's just say a very explosive personality, the alkali metals.
Okay, first, a super quick but really important term. When we talk about one of those vertical columns, we call it a group. And here's the key thing to remember. Elements in the same group are like siblings. They look a little different, but they have really similar properties and tend to act in similar ways.
So let's check out the family traits for Group 1. These metals are so soft you can literally cut them with a knife. When you do, they're super shiny, but only for a few seconds before they tarnish, because they react with the air almost instantly. And that last point there, very reactive, that is a massive, massive understatement, as you're about to see.
We'll start at the top of the group with lithium. You drop a little piece into water and bam, it starts reacting. You can see it fizzing, letting off hydrogen gas as it just kind of skates across the surface. It's a nice steady reaction. Pretty cool, but just you wait.
Next up, we've got sodium, which is right below lithium in Group 1. And whoa, it reacts way more vigorously. It zips around the surface like crazy, bubbling up much, much faster. You're starting to see a pattern here, right?
And then we get to potassium, the next one down. This is on a whole other level. The reaction is so intense, so energetic, that the metal melts into a tiny liquid ball, and the hydrogen gas it's producing actually bursts into this awesome lilac-colored flame. It is just a violent, fiery, and frankly, fantastic reaction.
Okay, so we've seen lithium fizz, we've seen sodium race, and we've seen potassium just catch on fire. There is definitely something going on here, a clear pattern. So now let's unpack the why behind all this escalating chemical drama.
This is the big question. This is what unlocks the secret code of the periodic table. Because what we just saw wasn't random at all. There's a beautiful, predictable logic to it.
And here's the secret, spelled right out. As you move down Group 1, from lithium to sodium to potassium, the reactivity, the sheer intensity of that reaction gets bigger and bigger. You see, the table's layout isn't just a random arrangement, it's telling a story.
Now, this predictable pattern has an official name. It's called a periodic trend. And the table is absolutely full of them. It's basically a cheat sheet that lets scientists predict how an element is going to behave just by knowing its address on the grid.
And oh yeah, this trend does not stop at potassium. The elements even further down the group, I'm talking rubidium, cesium, and francium, they are so ridiculously reactive that the explosions are just too dangerous to even show in a lab. The table predicted it, and reality proves it.
So you might be thinking, okay, that's a cool pattern for one group. But is that it? Is the table a one-trick pony? Not even close. This predictive power stretches across the entire map.
Let's jump all the way over to the other side of the table to Group 7, the halogens. Now, these are mostly reactive nonmetals, and they have their own trend. But here, as you go down the group, it's not reactivity that increases, it's their boiling point.
You can see it so clearly. At the top of the group, chlorine is a gas, so it has a really low boiling point. Go down one, and bromine is a liquid at room temperature. And go down again, and iodine is a solid with a much higher boiling point. It's another perfect, predictable pattern.
One last quick example, let's look at Group 0, the noble gases. Their main trend is that they don't react. They're famous for being inert, but they still follow patterns. As you go down their group, their density gets higher and higher. That's why helium, at the top, is light enough for balloons, while the ones further down are much, much heavier.
So you see, these patterns are so much more than just neat trivia. They are the fundamental organizing principle of all matter, and they give scientists a power that is, well, it's almost unbelievable. Just let this idea sink in for a moment. Scientists can predict the existence and the properties of elements they have never, ever seen, elements they haven't even created yet.
Those empty spaces you sometimes see on the table, they aren't just gaps. They're invitations. They're predictions of a discovery that's just waiting to be made, all thanks to the power of these trends.
And that brings us right back to our map. We've decoded one tiny little corner of it today, but it really makes you wonder, doesn't it? In these simple rows and columns that describe everything, from the air we breathe to the most distant stars, what other incredible secrets are still just waiting to be discovered?